welcome to the presentation. Thank you very much for the introduction. Let's dive into the different applications that we want to present you today. We have been having an increased number of people and labs in the forensic asking for HPTLC. This is not because the other methods are not used anymore, but because we have a high number of samples coming to these labs. HPTLC provides a high sensitivity and specificity crucial for detecting and identifying virus compound in forensic analysis. It is very fast because you can change the method from one to the other. You can do a lot of workloads and a lot of sample at the same time. As well, it is very cost effective. So compared to other analytical methods, HPTLC is cost effective. It requires less expensive equipment and reagent, especially maintaining the LCMS or the GCMS will cost you a lot. HPTLC is plug and play. If you don't use the system, it will not cost you anything. You turn it on, within 2 minutes, the system is ready. The other big advantage of HPTLC is the small or the minimal sample preparation. You can go with a heavy matrix on the plate, and as you use the plate only one time, you throw it away, but your system is not going to be clogged, or you have to clean your system after the analysis. Last but not least, in general, HPTLC offers you a visual documentation. This document can be taken to the court and offers a clear and understandable result for legal proceedings. So if we go to the first application with explosives, this has been elaborated and developed with Dubai Police. So Dubai Police already had a TLC application for explosive. We brought it to HPTLC. They wanted a fully automated method. We transferred the existing TLC method to HPTLC, enhancing the robustness and reliability of the analysis. We are able to analyze explosives and novel explosive on one plate. So while doing the analysis, you use one plate. Tin will explain you later the details of this application. So please, Tin, I will hand over. She shall do a nice presentation and explain you all the advantages of HPTLC with explosives.
Thank you, Raphael, for the nice introduction. So for the explosive, we will focus on two types of explosive. So we have the organic explosive. So you have the TNT, the PETN, the nitroglycerin, the tetryl, and the RDX. Then we have the peroxide explosives. So you have the TATP or the HMTD. Initially, there were two TLC methods, so two separate methods, the one for the organic and one for the peroxide. So you see that they are using both toluene and ethyl acetate as developing solvent. So they use exactly the same. Then for the saturation step, they are using 45 minutes and the developing distance is of 12 centimeters from the bottom edge of the plate. For the peroxide method, we had to dry the plate for 25 minutes. And then here it's where we had two different methods. It's because for the organic explosive, we had to derivatize with sodium hydroxide and then with the grease reagent. For the peroxide, we had to derivatize with 1% of diphenylamine solution. So when you look at the consumption of solvent, so it means that we had to use 100 milliliter for each plate. So in total, 200 milliliter of solvent. Then we had to wait for 45 minutes for the saturation, and then we had 30 minutes for the development of each plate. So the TLC methods are really solvent and time consuming. If now we look at the result and the RF value, we see that the nitroglycerin and the tetryl are quite close, and the PETN and the TATP are co-migrating. So here we see that the method was already not really good in TLC. So then in our study, what we have done is we have transferred the method from TLC to HPTLC. So for that, we use the same developing solvent, the same derivatization, and the same detection as the initial method. Then for the plate, the saturation and the activation step, we follow the HPTLC SOP from the HPTLC association. You have here the result for the TNT, the tetryl, the RDX, the PETN, and the nitroglycerin, so all the organic explosive. And then the second plate, we had all the peroxide explosive. So you see that we had a problem during our transfer of method. We see that the tetryl and the nitroglycerin are co-migrating, and the PETN and the TATP are also co-migrating. So the transfer of method was not easy. So for that, we had some solution. The first step is optimizing the HPTLC method. For that, we wanted to have only one method for the standard separation of all 7 explosives. Then we add also other detection in order to confirm the identification. So for example, the UV spectrum. We also did some additional tests to check if the quantification would be possible. For the sample preparation, we stay with the same as the initial method. For the sample application, we apply 2 microliters of each sample solution. And for the stationary phase, we use an HPTLC plate, a normal phase with a fluorescence indicator. For the optimization of the developing solvent, initially we had the method with toluene ethyl acetate 9-1, so the one that we have not a good separation. So we just had optimized the method with different selectivity. So we end up with a new developing solvent containing toluene, ethyl acetate, chloroform, and heptane. So you see here our result with the new developing solvent. We have a clear resolution between all the standard. So we have in the bottom the RDX, then we have the tetryl, the nitroglycerin, the PETN, and the TNT on the top. You see that the TATP is between the TNT and the PETN, and then the HMTD is above the RDX. For the second step, we have end up with another methodology, because the goal of our method was to use only one plate for both organic and peroxide explosive. So for that, we had the methodology. So the first step is to apply the same sequence on both sides of the plate. Then, so the step number 2, we develop the plate with the same mobile phase. Step number 3, we just cut the plate in the center with the smart cut. And then the last step is the derivatization. For that, you will use one side of the plate and you will derivatize for the organic explosive, and then the other side for the detection of the diphenylamine explosive, the peroxide explosive. Here it's one example of the plate that we have done. You see that on the left side, we have applied some sample and standard, and on the right side, we had applied also some standard and some sample. After the development, we record the UV spectrum of the detected zone. So here, for example, we can detect the RDX, the tetryl, and the TNT. And we have here those UV spectrums. So you see that the RDX has a maximum at 240 nanometers. The tetryl has a maximum at 233 nanometers, and the TNT has a maximum at 235. You see that the shape of their UV spectrum are different. The step number 4, we cut the HPTLC plate. So here on our example, we are just cutting the plate in the center. And then after, with the step number 5, we are derivatizing one side of the plate with the diphenylamine reagent, and then we will be able to detect all the peroxide explosive. The other side of the plate, we will derivatize here with the potassium hydroxide and the grease reagent, and we are able to detect all the organic explosive. So you see that the final result, we had a methodology that is quite simple, where you can have all the organic and peroxide explosive on the same plate. The results are quite good. The separation is sufficient for the detection of all the substance. And when we compare the consumption of solvent and time, you see that we succeed to decrease the developing time from 60 minutes to 10 minutes. The saturation time was decreased from 90 to 20 minutes. For the HPTLC method, we use 10 minutes of humidity control to be sure that the method will be reproducible. So at the end, for one plate, we decreased the time from 150 minutes to 40 minutes. When you look at the solvent consumption, we had 100 milliliter of solvent with the TLC method, and now we had 35 milliliter of solvent. I told you that we will do some additional steps. So for example, the quantification. Here, if we have, you see we have applied the RDX, the Tetril, and the TNT with different application volume to have a calibration curve. So here you have the 3 calibration curve from the RDX, the Tetril, and the TNT. And you see that it's quite easy to do some quantification if you need to do it.
Thank you very much, Tin, for this nice explanation on the explosive. Let's move on to the chemical warfare. The chemical warfare was developed in the last 2 years through a contact with a specialized army lab in Switzerland dedicated to detecting chemical warfare agent. It is a very sensitive topic, and of course, CAMAC doesn't have any standard in this direction, but this specialized lab offered us all the facility to develop this method. Again, it was a transfer from a TLC method used in the OPCW. The OPCW is the Organization for Prohibited Chemical Warfare. The method there was used, the primary method is a TLC method. After they move to the GCMS or to other method, but the screening is done with the TLC. The issue of such screening is when the source is unknown, thousands of samples need screening, and the HPTLC automation significantly speed up this process. So the case we had in England had over 33,000 samples to be tested because the person who been intoxicated, we couldn't say where they've been intoxicated. So in question were a restaurant, their home, of course, and the park. And you cannot keep close all these public facilities for months until the results are there. So HPTLC offers a very powerful tool for screening. The manual process have a high risk of contamination. The automation of HPTLC reduce this risk, ensuring reliable results and improving analyst safety. So this is a key thing that you don't have to work with a sample anymore. Once it's in the vial, you don't touch them. So please, Tin, explain this application to us, who is very interesting and brought us a very deep insight in this chemical warfare.
For the chemical warfare, we have 3 different classes of compounds. So we have the nerve agent, the blistering agents and irritants, and the arsenic agent. For the nerve agent, we had for the study 6 substances. So we had the GB, GA, GD, GF, the VX, and the RVX. For the blistering agent and irritant, we had also 6 substances. So the HD, TTA, CS, CN, CA, and CB. For the arsenic agents, we had 3 substances, the L, DA, and DM. The first step of our study was to transfer the initial TLC method to HPTLC. For that, we use the standardized parameters following the HPTLC SOP from the HPTLC Association. Then we optimize the parameters to reduce the number of steps, and we evaluate the quantification aspect. At the end, we had 3 individual methods. The first method is for the nerve agent. Here, we succeed to simplify the method by having only one developing solvent. Initially, the nerve agent are analyzed with 2 different developing solvent. And here we succeed to add all the 6 substances in only one method. We have here added the densitometry to measure the response and have some quantification also. Then for the blistering agent and irritants, here the transfer of method was straightforward because the method is using neat solvent, neat toluene has developing solvent. So here what we have just added was some densitometry to be able to quantify the zone after. For the arsenic agent, we have simplified the entire method by removing all the derivatization step because the 3 substances that we had were detected before derivatization. So here we just add some densitometry after the development to be able to quantify. If you look at the result here for the nerve agents, we have here the identification part. So you see that we have in the lower RF value the RVX, then we have VX, then you have the GD, GA, GF, and GB. You see that the resolution is quite good, and you have on the lower part the profile coming from the densitometry. If now we look at the quantification part, if we apply different application volume, for example, here for the GA, you see that we are able to generate the calibration curve. And from the calibration curve, we are able to generate or to estimate the LOD and the LOQ. Here you see that for the RVX and the VX, we can really go lower than 0.25 nanogram. For the nerve agent, we also develop another methodology for the large-scale integrated screening. So for that, actually what we wanted is to be able to detect the nerve agent without identification of the substance. So here what we said that was that you apply each sample that you have at different application volume, and then you don't develop the plate. You will just derivatize with the acetylcholinesterase, and you will be able to detect if it's active or not. So in that case, if you have a presence of nerve agent or not. Then if you see, for example, that is active and then that you have a presence of nerve agent, then you could do the first method to develop and then identify which nerve agents you have here. For the blistering agents and irritant, you have here the result for the identification part. You see that the HPTLC fingerprint on the upper part that we can detect prior to derivatization the CN, CS, and CA. After derivatization, we are able to detect TTA and HD. When we look at now the densitogram, we see that actually the CB and the HD are at the application position. So they stay at the application position. But when you do for the quantification part, you have the UV spectrum. You see that the CB and the HD has different UV spectrum, so you can discriminate them. Same thing with the UV spectrum, then you will be able to scan your plate at their maximum of absorption and then generate the calibration curve like here. You have this example of the TTA. The TTA has a maximum of absorption at 200 nanometers. So here you have in the center the peak profile from the scanning densitometry at 200 nanometers. And then after, on the detection C, you have the generated calibration curve. Then the last classes is the arsenic agent. So for the identification part, we have here the RF value obtained for each substance, and you have the HPTLC fingerprint here. And you see that actually in 254, after the development, you can detect the 3 substances. So you have the DM, then the L, and the DA. On the right side, you have the peak profile from the scanning densitometry. And the same thing for the quantification. You have the UV spectrum for each substance, and you see that they are really different, so you are able to discriminate them. And same thing, you are generating here all the calibration curve for each substance. So you will be able to quantify everything. So you have seen with the chemical warfare that we can detect all of them, identify, and then you would be able also to quantify each substance.
Thank you, Tin. This was a nice explanation, and I think everybody see the advantages of HPTLC in this case. But HPTLC don't offer you just two applications. Having a system in your forensic lab allows you to do a lot of other application. For example, the shooting distance measurement. When somebody gets shot and the shooter says he acted in self-defense, the distance between the shooter and the victim has to be measured. And there's a very effective way with a TLC plate to measure this. Then, of course, the drug of abuse screening. Many of you will say, well, we have LCMS to do that. This is clear. If you have one sample, two sample, or you can even take a very fast screening. But when you have hundreds of samples from a dealer already packed in a 1 gram bag, HPTLC can offer you a very fast way to prove that all 100 bags are, for example, methamphetamine or any drug of abuse. Long time ago, the US Secret Service developed a method for the identification of ink. So it identifies ball, pen, and printer ink, assisting in document forgery investigation and validating authenticity. So you can say if you have a pen around at somebody's house, you can prove that this document was written or signed with this pen, or you can assign a printer to a document. Then the cannabis testing was becoming very popular in the US and in Europe. We have, excuse me, we have a lot of legal cannabis where the THC is below 0.5 or in Switzerland 1%. And this testing has to be done on each and every sample. We can also see strains of cannabis or different kinds when you harvest and when you would have, if you need the THC, when you have the highest content. Then food poisonings, we have cases of cassava poisoning, for example, where manioc, it's called as well, where the people in the village are eating manioc who is has toxin inside, was not prepared well. So there we can check the raw materials on toxins. So as you see, we have a lot of application. One thing to know is that all the applications are on our homepage and you can download them free of charge. We can assist you if you need help there. And I'm really, really happy that you joined this presentation today, and I want to thank you.